Welcome to the second part of basic theory of fluid mechanics. In this lecture, we will try to see the Navier-Stokes equation, Bernoulli-Navier-Stokes equation. These are very fundamental equations when you study about fluid mechanics. Then its mathematical expression, application, and why does it matter? So, these 3 or 4 topics are very important. Then we will try to see about the Coyote equation, then Coyote flow, then its mathematical equation, application. Finally, we will try to see Hagen-Poiseuille flow, its mathematical expression and its applications. Navier-Stokes equation are a set of partial differential equations foundational to fluid mechanics. It is describing how velocity field of a viscous fluid evolves under the influence of various forces. This equation are named after C. Louis Navier and George Gabriel Stokes. They, in the 19th century, extended the earlier work of invisids, which is non-viscous fluids, by including the effect of viscosity, which accounts for internal friction within a fluid. So, viscosity comes, you have a thin layer of fluid which is sitting on top of it. So, this is any liquid which sits on a solid. So, the internal friction between the layers when it is flowing is the internal friction effect for viscosity. The picture whatever is here shows a hot air flown over a wing in a wind tunnel. So, wind tunnel are wherein which it is a tunnel where they try to simulate the air conditions like relative humidity. They try to increase the velocity wherein which they try to keep the object fixed. So, the air flow over a wing in a wind tunnel. It is a tunnel where wind velocities can be changed. You can go for Mach 1, Mach 2, Mach 3. You can have it varying temperatures. You can try to have it varying air densities, whatever it is. The little lines or smoke helps us to see the path of the moving air. So, this is the moving air. Some parts of the flow are smooth, while others may stand to swirl or separate from the wing surface. This is an example of what the Navier-Stokes theorem helps us to understand. How air moves, how it reacts to the shape of the object, how it creates the forces like lift and drag. So, all these things can be understood by going through Navier-Stokes theorem. So, the Navier-Stokes theorem, commonly referred as Navier-Stokes equation, is a set of partial equation that describes the motion of viscous fluid like liquids and gases. It is a partial differential equation. They are derived by applying Newton's second law of motion of fluid elements, taking into account the internal friction, pressure forces and external force such as gravity. That is all. They started with Newton's law of motion to fluids, right. There they started, and then finally they added internal friction and they gave the account for pressure forces, external force and then gravity, such as gravity. Describes motion. This figure which is given here describes motion of viscous fluid. The Navier-Stokes equation provides the fundamental mathematical framework for predicting how liquids and gases move accounting the real world effect like internal friction and pressure. So, you can see here there is an object moving with a velocity v, and then when there is it is trying to cut the flow of air. So, you can see there is a separation point which is happening, the flow separation is happening, that is there, and then you see how it tries to create a turbulence in the streamline. Based on the conservation of momentum, it is derived by applying the second law of fluid motions and expresses how momentum in a fluid element changes due to applied force, unifying the effect of pressure, viscosity and external force gravity. The extended previous fluid model by including viscosity, it extended Euler's equation for ideal fluid, making this equation suitable for real life and practical flows. So, conservation of momentum was taken and then the Euler's equation was extended. The central role in engineering and science, these equations underpin a wide range of fluid dynamic applications such as flow through a pipe, the air flowing over the wings, ocean current and blood flow in biology. Everywhere we use Navier-Stokes equation. Basically, we try to take pressure, viscosity and other external forces like gravity into the equation. The mathematical expression for Navier-Stokes equation in the general vectorial form is given like this. So, rho is the density, u is the velocity field, p is the pressure which is used, and then dynamic viscosity is nu, and then you have force acting on the body is F. These are divergent operators. So, in a Navier-Stokes equation, the forces on an element of an ideal fluid, so can be represented in this way. So, you have a gravity which comes down, then there is a pressure which is acting on an area. So, the pressure which is reaction force is represented like this. The alpha is the angle of attack. So, delta S is the length and minus delta H is the distance which is taken along the direction. So, the definition sketch for a fluid pressure and shear force, this is the unit cell. So, it is delta X, delta Y, and here there is a pressure, and then at the back the reaction force which is dP by dx into x, this is represent y and z. So, this is the shear, whatever happens is the tau. So, this is tau plus delta t u delta y into this, and this here you will the y term is not there. So, tau into delta x into delta y. So, the applications in engineering stream, water and oil flowing in a pipe or a channel, that can be found out by Navier-Stokes equation, designing of pump, turbine and hydraulic system, then airflow over a aeroplane wing or a car body. The natural phenomena of weather prediction is done by Navier-Stokes equation. The ocean current and waves, blood flowing, all these things are using Navier-Stokes equation. The scientific and in industrial use, many of the CFD simulators use Navier-Stokes equation. Environmental modeling, pollution, dispersion and river flow is also done by Navier-Stokes equation. The process industry, chemical reactions, reactors and heat exchangers, these are also done using the Navier-Stokes equation. So, the Navier-Stokes equation, it is a partial differential equation that describes the motion of viscous fluid, which is derived from Newton's second law of motion, wherein which they take into account of internal friction, pressure force, external forces such as gravity. So, that is what is given, force F. So, the Navier-Stokes theorem gives the mathematical rule that predicts and explains this kind of flow, how fluid behaves around the object. So, instead of a circular, if you have something like a serrated one object and the air is flowing through it. So, what is the influence and how does it happen? It tries to tell. Why sometimes the flow stays stationary and why sometimes the flow becomes turbulent. You see here there is a flow and then there is, it is a smooth flow and then it tries to exit, the lower stream and the upper stream meets and then goes. Sometimes what happens, there is a turbulence vortex which is getting created and the joining is postponed by a distance, right. So, that is what it is. So, the images is a simple visual representation of what the Navier-Stokes equation are used for in real time understanding and prediction. Why does it matter? Because it helps the engineer and the scientist to predict, design and optimize how fluid moves on top of a surface. On a practical system, how does it move? So, this is lift, this is drag, how does it move? So, then where is the separation happening? So, how does this separation happening and what is the effect? So, we saw the lift when it gets 100% full lift happening. So, central to solving real world problems in transportation, energy, health and environmental. This fluid flow through a pipe also we use Navier-Stokes equation. The image illustrates the behavior of the air over the airfoil at various angle of attack. So, you can see what happens when the angle of attack changes with the maximum focus on lift, drag and the resulting flow pattern. The Navier-Stokes equation provides a mathematical foundation that explains how and why this flow happens and how is it. Couette equation. The Couette equation arises from the study of Couette flow. So, what is a flow? It is always going in circular, which describes the lamellar flow of a viscous incompressible fluid between two parallel plates. This is a parallel plate, where one plate moves tangential relative to the other, induces fluid motion purely by shear stress. So, parallel plates, right, parallel plates where one plate moves tangential. So, you have a tangential, when the tangential relative to the other induces a fluid motion purely which is shear. So, you have the radius R1 and then you have radius R2 to the end of this plate, and then you see while rotating how does it create a flow. Okay. The Couette equation describes the flow of a viscous fluid between two parallel plates. When one plate is stationary, this is stationary, and the other plate is moving at a constant speed, it defines how the fluid flow changes in a straight line from the stationary to the moving plate. This type of fluid flow is called as Couette flow, which occurs due to shear getting created by the moving surface without any pressure difference deriving the flow. So, without creating any pressure difference, you move the top plate is moving with a velocity u and that creates a shear stress tau. So, the gradient which is going to be is du by dy. This image describes that one plate moves, one plate is stationary and the fluid is between the two slide motions from slowest to the fastest, because here it is 0, here it is fastest, is a perfect straight line. That is exactly what Couette equation describes. The Couette flow is a flow of viscous fluid confined between two surfaces where one surface moves tangentially relative to the other, causing the fluid to flow due to shear stress created by this relative motion. Typically, it involves two parallel plates or concentric cylinders. So, you can try to have a concentric cylinders where one held is stationary, the other one is moving at a constant velocity. This flow is steady, lamellar and primarily derived by the motion of a boundary rather than the pressure difference. So, basically we are trying to say this, if you go to look into this, so you can see the shear stress tau, how does it change, right? How does it change with respect to the distance where u is also changing. So, the Couette flow serves as a fundamental example in fluid dynamics to illustrate shear driven motion and is widely applied in engineering. So, we use in lubrication and in viscometer, and the natural phenomena modeling such as mantle and atmospheric flow, we do the cuvette flow. So, this is the cuvette flow analysis. So, the mathematical expression for a cuvette flow is, so here the moving plate is going at a velocity of 3 meters per second, and it is the between the two plates we have 1 meter. So, this is the stationary plate, this is the moving plate, and when there is a fluid flow through it, how does the flow profile happen? So, the velocity distribution of a fluid flow between two parallel plates, when the lower one is stationary and the upper one is moving, the velocity is u, which is expressed by this equation, where du is the fluid velocity at a displacement at the velocity at a distance y from the stationary plate, and u is the velocity of a moving plate, h is the distance between the two moving plates. The formula shows a linear profile across the two gaps. So, the assumptions are, the fluid is a Newtonian fluid with a constant viscosity nu, the lamellar flow between the two finite plates, flat plate and a parallel plate. One plate moves tangent with the velocity of u. So, the pressure gradient is dP by dx equal to u. The flow velocity depends on the coordinate of y normal to the plate. So, the applications of cuvette equations, it is used to measure the fluid viscosity. So, you have a axis symmetry section which is there. So, you are trying to rotate, this is a rotating plate. So, this is air, this is the distance, two stationary plates. Measuring fluid viscosity, widely used in viscometer, especially in cuvette viscometer, to determine the viscosity of the fluid by analyzing the relationship between the shear and the fluid velocity. Then lubrication theory, it is all derived by the cuvette equation. Modeling of thin film lubrication in bearing and machinery. Moving parts lubrication comes into very existence. So, the film has to be stable. When accurate prediction of the shear derived flow is important to minimize the wear and the optimized flow performance. Then the engineering design, useful for understanding and designing systems involved sheared fluid layer such as rotating cylinder, sliding plate and gap based on fluid devices. All these things we decide based upon the cuvette equation. The last part is Hagen-Poiseuille flow. The Hagen-Poiseuille flow is the smooth, steady movement of viscous fluid through a long, straight cylinder pipe with a constant cross-section area. This flow happens under specific condition where the fluid moves in parallel layers. Suppose you have a cylinder, so the fluid flows in parallel without mixing or the regime called as lamellar flow. So, the flow is derived by the pressure difference between the two ends of the pipe. So, this here the pressure and here the pressure. The flow is derived by the pressure difference between the two ends of the pipe, and the fluid's resistance to flow comes from the viscosity. So, through a pipe the fluid is flowing. So, that is what we are trying to see here in this flow. So, here you see a lamellar flow which is axis symmetry. You have this stream which is happening. When there is a pipe wall, the lamellar flow, you see how the parabolic effect is created on a non-axis symmetry flow. So, this is the axis symmetry, then it is a asymmetry, then you will have a turbulent flow which is happening inside the pipe. So, these are all various flow behaviors. This is lamellar uniform, this is lamellar non-uniform, and this is turbulent. The concept and the relative physical laws are discovered in the 19th century by Huygens and Poiseuille. It is the foundation of understanding how pressure, pipe size, fluid thickness, and pipe length affect the fluid flow in real time. For example, traveling through a pipe, straw and a medical needle. So, medical needle, you will have a needle which is like this, right. So, it is a, so here you have applying a pressure through a fluid. So, how pressure, pipe size, fluid thickness which is there, viscosity and the pipe length, pipe dia and length affect the fluid flow in many real world systems, ranging from blood moving through an artery to the other thing. It does not apply when the flow becomes turbulent or the pipe geometry is irregular. This Hagen-Poiseuille's flow does not come into existence. So, in essence, Hagen-Poiseuille's flow describes the viscous pressure driven lamellar flow of a fluid through a cylindrical pipe, showing how factors like pressure, pipe size, fluid properties affect the fluid flow behavior. So, it can be represented by this equation because it is flowing fluid through a cylindrical pipe. So, you have Q, volume discharge rate, is nothing but pi times delta P, which is a pressure difference between entry and exit. R is the radius of the pipe divided by 8, and this is dynamic viscosity, and then the length of the pipe is this. So, through which we can try to find out what is the relationship between the volumetric flow rate Q with respect to pressure, radius, length and viscosity, dynamic viscosity of the fluid. So, the applications are many. It can be used to determine the flow rate of IV fluid based on cannular size and fluid property. It helps in optimizing cathedral size and length for efficient and safe fluid administration. If you see very closely the blood in biomedical applications, these flow behaviors are very important. The blood flow in arteries and veins, it can be modeled through this equation. It is important to understand the vascular resistance and the conditions like constricted arteries. Then the pipes and fluid flow transportation aids in designing pipelines by calculating the pressure drop, diameter and the pumping requirement. So, you can see here high pressure, low pressure, there is a pressure drop which is delta P. The fluid is flowing through. Ensures efficient transport of the fluid such as oil, water and chemical over a distance. So, to recap in this lecture, what we saw was, we saw about Navier-Stokes equation, importance about Navier-Stokes equation or theorem, then Couette equation, then its importance, then Hagen-Poiseuille's flow, then its application. So, here it was moving plate, fixed is Couette equation. Here it was moving through a pipe. This is stationary and this is moving. So, here it is a pipe. So, we saw the flow behavior and for which we saw the equations. These are some of the references which we have used for this lecture, and thank you very much.